Okay, this is exam 2 for physics 201 from fall 2011. Which of these statements best describe Aristotle's view of the natural world? Alright, all objects are propelled by a mystical force that emanates from the earth. That's not one. All objects have a natural state, which is at rest. Alright, that is what he thought, but let's look at these others. Objects will continue in motion unless an outside force acts on them. That was Newton's view, Newton's first law. The mass of an object is a measure of its inertia. That was also Newton's view, so the answer is B. Which of these makes up the basic SI units of the Newton? Newton is measure of force, which is mass times acceleration. That's going to be kilograms times meters per second squared. It looks like it's B. From rest, we step on the gas of our Subaru, providing a force for 4 seconds, traveling a distance of 10 meters. If the applied force were only half F, how far does the car travel in the same amount of time? So with a force half F, that means that we have half the acceleration, because remember F equals ma. If we have half the force, we have half the acceleration if the mass stays constant. And we want to know how far does the car travel. We know x is equal to 1/2 at squared. If our acceleration is half its original value, and we travel the same amount of time, that means our displacement is going to be this half the original distance, so it's 5 meters. That's C. A block of mass m rests on the floor of an elevator that is accelerating upward. It's going up. What is the relationship between the force due to gravity and the normal force? So the normal force is going to exceed the weight. If it was traveling at a constant speed or stationary, it would equal the weight. If it was falling down, the normal force would be less than the weight. But in this case, it's going to exceed the weight. That's A. Fn is greater than Fg. Which of these is a conservative force? Any field force is conservative. Any force that requires contact is a non-conservative force. Field forces include gravitational, electric forces. That's 1 and 3. So that's D. Which is usually larger, kinetic or static friction? B. In this figure, all the blocks have a displacement to the right. The magnitude of the force is the same for each block. Which force is doing no amount of work? Alright, the one that does no amount of work is the one that's perpendicular to the displacement, because remember it's FD cosine theta. Those are 90 degrees apart, and the cosine of 90 is 0, so it's A is number 7. Car travels a distance x at an acceleration a and does work w. If the car travels a distance 2x at the same acceleration, what work has it done? What work has it done? Or what work is equal to the force times the displacement. Since it's traveling at the same acceleration, the force is going to be the same. It's just traveling twice the distance, so that's going to mean twice the work. Which requires more energy? Take a car from 0 to 30 or 30 to 60. Remember, if we plot our kinetic energy versus speed, it's a parabola, 1/2 mv squared, v squared. So 0 to 30 takes this amount of energy, 30 to 60 takes a lot more energy because it's a v squared dependent. So 30 to 60, that's B. Consider this figure. 3 blocks of mass m slide down different inclined planes, each beginning at a height h. They all have the same coefficient of kinetic friction, 0.3. Which block has the most energy? Alright, you have friction in this case. At the top, they all have the same amount of potential energy, but the one that travels the further distance loses the most amount of energy. Alright, so this one loses more energy because it travels a greater distance, and that frictional force, a non-conservative force, is acting, which is a path-dependent force. So it's going to be the one that travels the least distance has the most energy. That's A. You can press a mass on a spring, as in this figure, and release it. At what position does the mass have its largest speed? You have its largest speed where its potential energy is equal to 0. So all the energy is in kinetic energy. Alright, so that's at x equal 0. That's B. Which of these statements is most appropriate for an elastic collision? In an elastic collision, like the collisions between gas molecules, for example, energy and momentum are conserved. That's B. A uranium nucleus at rest undergoes fission and splits into 2 fragments, one heavy and the other light. Which fragment has the greater speed? They both have the same momentum, so the smaller fragment, the lighter fragment, has the greater speed. A collection of particles has a total momentum of 0. Which of these statements is true? Just because the momentum is 0 does not mean that they're at rest, because momentum is a vector quantity. So it doesn't mean that the kinetic energy has to be 0. Let's see, we can just go through. The particles have no mass. It doesn't mean that. Kinetic energy of the particles must be 0. Definitely not that it doesn't have to be 0. They can be 0, but not necessarily. The particles are definitely moving. That's not true either. But the kinetic energy of the particles might be 0, but not necessarily. That's D. An open cart rolls along a frictionless track while it's raining. As it rolls, what happens to the speed of the cart as the rain collects in it? As the rain collects in it, the mass is going to increase. That means that the speed is going to decrease in order to maintain constant momentum. So it slows down. That's B. Alright, consider this figure. The coefficient of kinetic friction between block number 2 and the inclined plane is 0.1. What is the mass of the block number 1 to give the acceleration? So, I want to draw my vector diagrams. I have force weight and force tension. This is FW1. The acceleration for 1 is equal to 1 meter per second squared. And then if I draw my forces over here, I have force weight, force normal. I have the kinetic friction, the tension, and that's all. This is force weight 2. Alright, and the acceleration is 1 meter per second squared. Now I'm just going to write out my vectors, or I'll draw my vector diagrams. Let's see, I have, on this one, I just have Ft up and FW1 down. And then over here, I have Fn, Ft and Fk. And then I'm going to go ahead and take the components. This is FWT cosine of 60, FW2 cosine of 60, and FW2 sine of 60. Those are the x and y components of this force vector. Remember, this angle is 90 minus 30, which is 60 degrees. Now I can write out my my Newton's second law for each of these. Looking here first, Ft minus Fw1 is equal to m1 times a. And now continuing on with these, I'll do the y first. Fn minus Fw2 sine of 60 is equal to m2 ay, but that's equal to 0 because it doesn't move in the y direction in that coordinate system. And then the second is Fw2 cosine of 60 minus Fk minus Ft is equal to m2a. And the acceleration for both is equal to 1, just 1 meter per second squared. Now, I first want to find my normal force. And I've sort of laid out the procedure over here. So I want to find my normal force. Fn is equal to Fw2 sine of 60. Fw2, that's 10 times 9.8. The mass of the second block is 10 kilograms. Sine of 60. That's 98 sine of 60. Gives me 85 newtons. So the normal force is 85 newtons. And then I need to find my kinetic frictional force. That's mu k Fn. That is 0.1 times 85. That's 8.5 newtons. And then I want to find my tension force. So what is Ft equal to? Well, let's see. I know my normal. I can use this. Right? Yeah, I can use that in order to find the tension. So the tension force from that third equation is equal to Fw2 cosine of 60 minus Fk minus m2a. And Fw2, that's 10 times 9.8 times the cosine of 60 minus 8.5 minus m2, which is 10 times 1. That's 49 minus 8.5 minus 10. we get 31 newtons. So Ft is 31 newtons. Let me go ahead and write these in. 8.5 newtons, and then Fn was 85 newtons. And then I finally want to solve for the mass. Mass 1. Well, that's in this equation right here. So I can solve for mass 1. Now that I know the tension, I have Ft equals m1g plus m1a. And so m1 is equal to Ft over g plus a. That is 31 over 9.8 plus 1. 31, and I get 2.9 kilograms. 2.9. Alright, this figure shows a 1 kilogram mass on a spring with a spring constant of 550 newtons per meter that is compressed by 10 centimeters to the left of the equilibrium position. Immediately to the right of the equilibrium position, there is a region where the frictional force is present. This force is dependent upon the position as given. The region extends 4 centimeters to the right of the equilibrium position. Alright, what is the initial total energy of the system? That's simple. It's just the potential energy. It has no kinetic energy initially, so it's 1/2 kx squared. That's 1/2 of 550. Times x is 10 centimeters or 0.1 meters squared. And that gives me the potential energy, which is 2.75 joules. 2.75 joules. And then B, after release, what is the speed of the block at 5 centimeters to the left of the equilibrium position? So I want to know what is the speed of the block at that point. Now at that point, its energy is constant. It's equal to 2.75 joules, and it's equal to, well, let's do this a slightly different way actually. Let's say that the initial potential energy is equal to the potential energy plus the kinetic energy at that spot. Let's see, that's 2.75 joules is equal to 1/2 kx squared, where x is going to be 5 centimeters, plus 1/2 mv squared. And then I need to solve for v, and this I'm going to put in some numbers first. 1/2 of 550 times 0.05 squared, that's 5 centimeters. I'm at 5 centimeters right here. Plus 1/2 of 1 kilogram times v squared. And let's see, that gives me 2.75. I get 2 meters per second for V. So solving that for V, I get 2.0 meters per second. And then how much energy is lost each time the block goes through the force field region, or through this through this region, this 4 centimeter region where you have this dissipative force. That's equal to the work. It's equal to the integral of f dx. That's the integral of 5,000 x squared dx, which is going to be 5,000 x cubed over 3 over my limits of integration, which are from 0 to 0.04 meters. And applying those limits of integration, 5,000 0.04 cubed divided by 3. See, I get 0.11 joules. Just a second, let me check this number again, because this is different from my notes. 5,000 0.11 joules. So that's the amount of energy that I lose. It's the amount of energy that I lose. And then I want to know just how many times it goes through this patch. It loses energy each time it goes through. So to find the total number of times that it passes through the equilibrium position before it comes to rest, I just divide the total energy, which is 2.75 joules, divided by the amount of energy that it loses, which is 0.11 joules. That's 2.5, so 2.5 times. Really is going to go through one time fully, and then it'll come back and stop in the patch. Or excuse me, 2 times fully, and then it'll come back and stop in the patch. I would take either 2 or 2.5. Okay, that's number 17. Number 18. A force acts on a particle which is initially at rest. The force is 3I plus 4J, and the particle is initially at DI is 0.25 plus 0.5 J meters. After 2 seconds, it's located at this new location. How much work has been done by the force? Well, first we need to know what is the net displacement. That's just dF minus DI, which is going to be 3.25 minus 0.25 in the I direction, plus 4.5 minus 0.5. Just subtracting the x and y terms in the j direction. And so that gives me 3I plus 4j. And then to find the work is just F dot D. The force is 3I plus 4j. Oh, and then you're dotting it with 3I plus 4j. That's equal to 9. That's 3 times 3, I dot I is equal to 1, plus 16 is equal to 25. Joules are Newton meters. Then we want to know how much power is provided by the force. Well, power is just work over time. That's 25 joules over the time, which is given 2 seconds, which is 12.5 or 13 watts. C is what is the mass of the particle, and I give you a hint that x is equal to 1/2 AT squared. Alright, so x is equal to 1/2 AX t squared. In the x direction, it travels 3 meters. That's equal to 1/2 times the mass or the acceleration in the x direction times the time that it does this, which is 2 seconds. Alright, so I can solve then for AX. See, that's 6 over 4. Or excuse me, I can solve for, I know that, well, let's do it this way. So I get A is equal to 6 over 4, which is 3/2 meters per second squared. And then I know that Fx equals MAX. And Fx is given. It's 3I is equal to the mass times 3/2. That means that the mass is 2 kilograms. And then finally in D, what is the magnitude of the final velocity of the particle? Well, I know that the work goes into energy, which is going to be 1/2 mv squared. And so I say 25 joules is equal to 1/2 times 2 times v squared, and I find that v is equal to the square root of 25, or 5 meters per second. Alright, last problem. Oh, still need some edits on this problem. What do I need to do? Okay, well, I've already made the edits in on the test. So I have 2 particles collide, and then just forget this. I'll change it before I print it. 2 particles collide. Their initial conditions are as shown in this figure. After the condition, the second particle travels at 0.5 meters per second in the positive x direction. So my VF for this one is equal to 0.5 J. What is the final velocity of the first particle? Give the magnitude and direction of this velocity. Actually, I left this off, so I just wanted, on your test, it said just to give it in vector notation. So I just start with my conservation momentum. Pi is equal to Pf, and the Pi is going to be just the first particle, that is m1 v1I, and then it's going to equal m2 v2f plus m1 v1f. And I want to know this final velocity of the first particle, so I want to figure out what that is. I know everything else, so it's really just algebra, but I have to be careful to keep everything in vector notation. So let's just go and write it in. I have 2 kilograms times 3I minus 4j, that's in meters per second, equals 4 kilograms times 0.5I, this should be I, that's in meters per second, plus 2 kilograms times v1fxi. Alright, that's the final speed of particle 1 in the x direction, plus v1fyj. That's the final speed of particle 1 in the y direction. And then I just have algebra, so I have 6I minus 8j equals 2I plus 2 v1fxi plus 2 v1fyj. And then I combine my I and j terms, so that I'm just going to take this over to the left-hand side. I get 4I minus 8j. I'm going to go and divide both sides by 2, is equal to v1f in vector notation. And that's equal to 2I minus 4j meters per second, and that's v1f. That's the answer. There's the multiple choice.